Roger, let's do a retrospective on black holes. And here, it's not so much that you challenge the conventional wisdom of black holes, but you were a major key in creating the now standard model of black holes. So I'd like to kind of go back through the history. And as we know, Einstein's general relativity and 1915 was obviously the key element. Then, in the same year, remarkably, Carl Schwarzschild and in the trenches of World War I came up with a solution, a specific solution to Einstein's equations, which led to the Schwarzschild radius and black holes, and then Oppenheimer 1939. So, in that sequence of activity, how did you get involved in black holes? And what was your key insight that developed from Einstein, Schwarzschild, and Oppenheimer that you brought to it?
Well, I certainly knew about the Oppenheimer-Snyder paper, which I think it was what triggered it was the quasars. You see,
Oh,
there was a great activity and puzzlement because of these enormously bright signals. Well, I say bright, I guess in the radio initially they were. And not only they were enormously strong, but they were enormously redshifted. There were changes also occurred within periods of, I think, weeks, which was regarded as a short time.
very.
Meant that the bodies had to be very small compared with how much energy was released by them. And so
Mm.
people, I remember Fred Hoyle and other people. I mean, Fred Hoyle was somebody I knew quite well. Of course, he had views which were not the common ones in many respects. Certainly, there was this general puzzlement about these objects which seemed to be, I mean, there was still a fair amount of argument as to whether they were really redshifted by local gravitational field, and they weren't really as distant as they seemed to be. I don't think that got much credence, but there was a view of
Right.
possibility. It seemed to be that they were very distant and very massive, and therefore you had to run into this problem that Oppenheimer and Snyder had run into. Of course, their solution was exactly symmetrical. You had a body which is focused right into the center. Everything was aimed at the central point, and so there's no escape. It's singular. You've got this singularity of infinite density in this state. But people argue, well, look, that's not very realistic. It's going to swish around and maybe come swirling out again. And that's perhaps the sort of thing you get. Or what? And I think the view tended to be that the thing swished around and came swirling out again. There was a paper at that time by Lifshitz and Khalatnikov, two Russians. And in this paper, they seem to have proved that in the general case, you would not get singularities. And that was the common belief at that time. I went and had a look at their paper. I did not find their arguments all that persuasive. They were not kind of the thing that I would find really as a rigorous proof. I didn't notice the mistake. There was a mistake, which was, I think, found by Belinsky later on. And Belinsky then collaborated with them and came to the opposite conclusion. But this was later. This was after my result. What I'm saying about my result, I had been thinking about global things in relativity already for some other reason. I can't quite remember what it was. I think it was to do with asymptotics. I was thinking about general arguments where you look about light cones and what you can say, but not really solving the equations in general, but looking at general arguments in general relativity. So that was the sort of connecting point. Then I tried to think about black holes, but I wondered about the singularity question, thinking about, I had a little bit of an open mind at the time. Maybe Lifshitz and Khalatnikov were right, and that you didn't get singularities in general. Maybe they were wrong. I tended to think probably they were wrong. I don't quite know why I thought that. And I remember walking through the woods near where I used to live and trying to think. It was rather nice to walk into the woods and to think about what it would be like inside one of these collapsing situations. And would you be able to characterize what had gone wrong? Could you say when it had gone wrong? Is there some characterization of what was, how would you characterize it's wrong? And this is the sort of story which I used to talk about later on, I was talking about walking towards my work in Birkbeck College at the time, and I was accompanied by Ivor Robinson, who was an Englishman who had a wonderful way with words. The Americans loved him because he had this wonderful way with words. And he went and lived in the US afterwards. I think he was only visiting England at this time. But anyway, he had lots of good ideas in relativity. He never wrote anything down. He was good with words, but not in the print, if you're verbal words. Somebody else had to do the writing up. It was almost entirely that way. So he needed a good collaborator, which was usually Andre Troutman, I remember. But anyway, he was talking to me about something or other. I can't even remember what it was. And we reached this side street close to where I worked. And at that point, the conversation stopped. I'm sure I've told you this story, or I've told it many times. Conversation stopped. And then when we got to the other side, the conversation started up again. And then when he went off and did something I can't remember, I think he had some other appointment, I went to my office, and I remember feeling this strange feeling of elation. Why do I feel so chirpy? What's going on? And I went through all the things that happened in the day, walking through the woods. No, wasn't that. Walking down from the bus, that walk down there. No, it wasn't that. Oh, it must have been that moment of crossing the street. And what was it? And then it came back to me what the thought was I had crossing the street. And it was evidently the idea of how to characterize that a collapse had gone too far in a way which was a generic statement. It wasn't any statement about curvatures or anything like that. It was about focusing of light rays. And I knew quite a bit about boundaries of futures. You see, my earlier work on thinking about general arguments, one of the things was thinking about future sets. I'd have to carry what I mean by that. You'd have the future of a set. You've got some localized set in space-time, in space and in time. And what is the set that you can reach from that place by light rays and causal lines, that is to say, lines which don't exceed the speed of light? And what is the boundary of that region? What does that look like? What characterization does it have? And so I knew, I worked on this a bit, and I knew something about it. I knew something about it had to be generated by light rays, and these light rays had to go back and meet something or other. And so I knew enough about that to see that this idea that I'd had of crossing the street could be used to get you some statement about the singularities in collapsing models. So what was the characterization? It was a thing I called a trapped surface. So this is a two-dimensional surface, which is space-like. So it's like an ordinary surface in space, which has the curious property that if you have a flash of light on that surface, see, if you might imagine it's convex on one side and concave on the other side, then if the flash of light would go inwards on the concave side and outwards on the convex side. If it was hyperbolic, they might go inwards some ways and outwards some ways and inwards in other ways. Now, a trapped surface is something where it's inwards both ways. And you might think that's a contradiction. How can it be concave on both sides? It's not a contradiction, because if you imagine the intersection of two light cones, then where they intersect, the light rays do converge because they're coming from 2 points. Well, this way, I'm thinking the opposite way around. I think that's way. You're imagining the intersection of two past light cones. As they intersect, that surface which they intersect in, which is a space-like surface, the light rays orthogonal to that surface are converging in both ways. So it's not locally a contradiction. There's nothing wrong with it locally. However, what is contradictory, in a certain sense, is both having this light rays converging on both sides, but on being on a compact surface. So this two-dimensional surface, which you start with, that's the trapped surface. The light rays from it, you imagine a flash of light on that surface, bang, flash of light. And the boundary of that region, the light rays are converging on both sides. Why is that a problem? Well, then I knew enough about how the boundaries of futures look like, and blah, 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 and I realized we were in trouble. And that trouble was the basis of this paper I wrote, which was, it didn't take me long to work it out, write this paper, which was published in Physical Review Letters. I think the word singularity appears in the title, but nowhere else in the paper, as far as I remember, because it's not a singularity necessarily in the sense that curvatures go to infinity. It's a singularity in the sense that something goes wrong. You can't have an ordinary space-time. It might be that light rays go round and round in circles, or blah, 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 blah. It might just be that the surface you start with doesn't contain all the information. And there are things like wormholes that were really invented by Kip Thorne in order to try and explain how universe might join onto another universe or something like that. And things like that, which are not singularities in the sense of curvatures going to infinity, but they are singular behavior in the sense that I get the nice solution. So that was my paper. It did create a lot of fuss. Various people didn't believe me. I remember one of the people who didn't believe me was Jim Bardeen. He had the problem of having a father who got 2 Nobel Prizes. And so all the time he was trying to battle against his father in some way, I think. And so he was battling against me and saying my argument was all wrong. And I remember he said that we haven't got the point at all. I told him he was quite wrong. But you see, that it was an argument that wasn't quite singularities in the curvature sense. And so you have to get that straight. And it was also, I remember another anecdote. I was visiting Princeton and describing, no, I wasn't, I was about to give a talk on something, I can't remember what. I was attending another talk and I was thinking outside the lecture room, just waiting. I was waiting for the talk, for the lecturer to become free. That's right. And Bob Dickey, who was a great figure in cosmology and things like this, and he slapped me on the back and he said, "You've done it. You've shown general relativity is wrong." And that's what I thought I'd done. But the reason was he had his own theory and he wanted to make this theory supplant general relativity. What he didn't realize was his theory suffered from just the same problem. You could have trapped surfaces and just this doesn't make any difference. But still, it was.
But a key point is that the singularity is not what we typically think, where the mass becomes infinite and infinite curvature,
Yes.
but meaning a singular event that we don't know what it is, but it has to be something
It has to be
that's
not
unique.
the ordinary evolution of a space-time.
Right.
Something goes
Right.
wrong. And there are examples where what goes wrong is much more exotic, but very special. I think there may be, I always thought there would be a theorem I didn't have of my own, which showed that in the generic case, you would actually get curvature singularities. And I believed that to be correct. That is, if you perturb your solution, that these special ones which don't go singular are very special. And a little perturbation of those makes it really singular. And I think there is a paper, I haven't tracked, I've been out of touch with the way the subject has gone. I believe that somebody that has developed that subject and shown some theorem of that nature.
So over the decades since your seminal paper, have your views on what that singularity, that singular kind of event is, has it changed? Many people obviously speculate on what that is.
I don't think it's changed from what I really believed then. I mean, there were certainly these funny models where you get things swirling around, time paradoxes and non-uniqueness and goodness knows. I think I believed that the generic case would be singular. And I think I said this in the paper and gave a sort of an outline of some argument which I thought might perhaps give one. It wasn't a proof. It was a line of thought that might be developed into a proof. I've been so out of touch with what's going on in the subject that I got a message that somebody has an argument of this nature, which I haven't followed up on. So this would prove what I tended to think before, which was that curvature singularities were what almost always would happen. None of this other crazy stuff would be likely to happen.
Mm. And what would be the implications of that? What follows from it?
Well, you see, people would say quantum gravity. So here's where I have a little bit of a different viewpoint from many people. See, people say, what is the major thing in physics which we don't know? Quantizing gravity. And this would be trying to resolve what happens in a black hole. Okay, yeah, I agree that something's got to be said and resolved, but it may not be any decent kind of space-time. It may just be that is the end, that space-time terminates. Many people aren't happy with that. But you see, even if you get around it with quantum gravity, no, these equations say that blah, blah, blah happens. Well, maybe blah, blah, blah happens, but it's not going to help us very much. You still have black holes. Blah, blah, blah isn't going to do us anything for the outside of a black hole. So it's not the real problem. The real problem is not quantizing gravity. The real problem is gravitizing quantum mechanics, because quantum mechanics has this big blemish. The blemish is the collapse of the wave function. That's not part of the theory. The theory doesn't have a thing which it says, which it's not even something which happens in exotic situations like black hole. It's all the time. It's what you need to make the theory make sense. The theory still doesn't make sense, because if you follow the Schrödinger evolution, you don't get the right answer. The right answer is what the world does. By the right answer, I mean what the world does. What the world does is not follow the Schrödinger equation. It says, I've had enough of your Schrödinger equation stuff. I'm doing something else. I'm collapsing the wave function. What's the theory of that? That's what we need. That's the major missing thing of physics. I strongly believe that. And I don't know why people don't.
And are black holes sort of a test bed, a laboratory for exploring the collapse of the wave function?
It's not obvious that they are. I mean, the good theory of black holes is needed. I'm out of date, although I have been in conversation with Remo Ruffini about this, and maybe he can help me out, which has to do with, you see, there's not just the Kerr solution, which is this wonderful development and rotating black holes, but there is what's called the Kerr-Newman solution. I'm a little bit puzzled by why it's called the Kerr-Newman solution and not just the Newman solution, because the Schwarzschild solution isn't called the Schwarzschild-Einstein solution. Well, I should have put it that way, not that. It's the Reisner-Nordstrom solution. It's not called the Reisner-Nordstrom-Schwarzschild solution. It's called the Reisner-Nordstrom solution. Never mind, that's a quibble. Anyway, the Kerr-Newman solution is what happens for a rotating black hole with electromagnetism. And you've got to have that, because the extraordinary thing that you see in these quasars, and that goes back to the story that puzzled everybody, and what this enormous amount of energy comes squirting out. If it's just black holes, they don't squirt energy out. They just sit there. It's a dumb thing. What's the good of them? If they rotate a bit, you could get energy out by this thing, which is called the Penrose process, or the Zeldovich-Penrose process. I'm not quite sure well. He did it for fields, and I did it for particles, I think. Never mind. But this is how you can extract energy from the rotation of a black hole. Sure. You can get energy out of the rotation of a black hole. And I used to write papers on that stuff. But you've got to get it out in a way which is all tied up with electromagnetism and all tied up with it being focused along the axis, which is presumably to do with the fact that the energy comes out without affecting the angular momentum. It comes out along the axis. And so that's the way to do it. If you don't want to affect, you want to use the angular momentum and convert that into energy by this process. And then you squirt it out along the axis. And as long as you can keep as much angular momentum as you can, that's a good thing to do. And then you change it into the energy which squirts out. And that's this amazing. I don't know what the theory of quasars is. Maybe it's all explained perfectly well now and people understand it perfectly. But that's the nearest I could say one gets to they're not singularities, but they're pretty extreme case situations along the axis of a rotating. You see, I had various crazy wrong ideas at one time about singularities maybe being visible in some circumstances when the thing rotates. You see, if you take a Kerr solution which rotates too fast, it's not a black hole anymore. And so some people used to argue that maybe that's the situation, and then you can see the singularity. But that sort of kind of model isn't realistic in the sense you don't see how it would evolve. It's the black holes which evolve, not those crazy Kerr solutions which have more angular momentum, or more A than M. The AM is the angular momentum, which works rather nice as an acronym. AM is angular momentum, Km is the mass, and A is the Kerr parameter. But then you've got a charge as well, and then that gives you a Kerr-Newman solution. And the Kerr-Newman solution is the thing you need to study, presumably, in order to understand quasars. Maybe people understand it all. I'm out of touch with what's going on in the world. I don't know.
Thank you for watching. If you like this video, please like and comment below. You can support Closer to Truth by subscribing. Closer to Truth is now accepting your tax-exempt donations. Please come to closertotruth.com/donate. Thank you very much for supporting us, and thanks for watching.